Hi, in the last session, we talked about VHDL process block and if-else statement. Now, in this session, we will be talking about VHDL components and how to instantiate them in the VHDL structural design. So, let's start. Okay, so till now, we have designed some standalone VHDL entities and we write the architecture for them. Hence, everything is in a single file. Now we are going to explore that how you can combine two or more entities to create more complex designs. Alternatively, you can say that how you can use your existing VHDL designs as a component in a bigger system. Now look at this simple VHDL module. So we have this VHDL design which is named as sub1. This module has two input signal. One is sig A and another is sig B, and it has one output D out. And let's assume that this module is doing the addition operation. We are not mentioning the data type at the moment, but we will define them in some time in our code, so don't confuse. This means we are writing a VHDL code for a module which has two inputs, sig A and sig B, and you will be getting the output D out, which is sum of these two input signals. Simple. Now look at this block diagram. So suppose we have developed this entity sub1 as we talked in our last slide, and now we wanted to use this existing module in our another design. So you can say that you wanted to use this already developed VHDL design in some bigger VHDL design. Now the name of this big system is suppose top level entity, and it has input signal X and another input signal Y, and it also has one output signal which is D out. Now in this top level entity, you wanted to use sub1 design as a small element. This is what we are going to do in this session. In VHDL, we call this component, means sub1 will be used as a component of a bigger VHDL module named as top level entity, or in general, you can say it instance. So you can see in the slide that you can use your component multiple times in your top level entity. There is no limitation to that. For example, we are using the same component of sub1 two times in this top level entity. You can use different components and you can also use them as many times as you need it. This approach is helpful when you are designing some big architecture in VHDL, or if you are going to use some modules very frequently in your designs. For example, you are designing a microcontroller which has multiple elements inside it, like it has arithmetic operation unit, it has counters, it has serial communication module inside it, it has memory, it has timers, etc. So instead designing all of these elements inside one big VHDL module, you can prefer to design them separately in separate VHDL modules. And once you have developed them and test them separately, and once you are ensured that each and every module is working fine, then you can combine these all modules in one single VHDL design. And hence it will ease your whole design process and also testing process as well, because now you can test your individual modules, and if any module has some bugs, then you just need to look at this problematic module, not the whole big architecture. Another benefit is that if you have a team of people, then you can share your modules between them, which will ultimately shorten your designing time. Also, if you're using some modules very frequently in your other designs, then you do not need to write them again and again. You can just design it once and then you can use them multiple times as a component in your top level entity. So these are some of the benefits of using components in your VHDL designs. So you can see this block diagram now. This is very clear. We are using two instances of sub1 entity in this top level design. This has some internal signals as well to connect the component ports with the wires or signals of your top level entity. So let's quickly brief this because we are going to write a VHDL code for this design. So we have two components of entity sub1, which are component 1 and component 2. Component 1 has signal sig1, sig2 and sig3, which are connected to sig A, sig B and D out respectively for component 1. Next is component 2, and it has signals sig4, sig5 and sig6, which are connected to sig A, sig B and D out respectively of component 2. top level module has two inputs, sig X and sig Y, and one output, D out. In the next slide, we will see that how these component ports are internally connected with the wires of top level entity. But before we write the VHDL code for this, let's have some quick recap of how we write the VHDL codes for our designs. This is simple template for a VHDL module. First is library declaration section at the top. Here you need to declare all the libraries and packages which are you going to use in your VHDL design. For example, library IEEE. Then write library IEEE semicolon use IEEE.std underscore logic underscore 1164.all semicolon. You can write more packages as well. Now the next is entity declaration. This section defines the name of entity and its input and output ports. Then we give the architecture declaration. This has two sections. One section is between the architecture statement and begin statement. And another section is between the begin statement and end architecture statement. So section 1 is called declaration part. Here you will declare all the signals and constants which are needing for your project. Note that here you need to declare components as well, which we are going to use in our designs, which we are currently discussing. So note that we need to declare those components in this section here. Next section is architecture body, where you will define your module behavior and you will write the functionality of your project. Now let's come back to our component topic. So look at this architecture view of our top level design. So first we need to know that what this entity sub1 will do here. As I said, this sub1 entity is doing the addition operation on the integer number. And this module is able to add any two numbers which can have any value between the range of 0 to 9. Okay, now in this top level entity, we are using two instances of this component. Its first instance taking the input from the top level entity and giving the sum at the output. And then the output of the first instance is being used as an input to the second instance of component and giving the output. Note that we are giving the same input on the both ports of the component 2. Now the output of component 2 is directly connected to the output of our top module. I hope the requirement is clear to you. If this is clear, then let's write the VHDL code for this. Please note that we are writing them in parts to explain things one by one, and then we will combine the whole code in the last. So we will start from writing the VHDL code for our submodule, which is sub1. So here is the VHDL code for this. Entity sub1 is port A colon in integer range 0 to 9 semicolon. B colon in integer range 0 to 9 semicolon. D out colon out integer range 0 to 36 bracket close semicolon and entity semicolon. Architecture behave of sub1 is begin D out gets the value of A plus B semicolon, and this performs the addition operation as mentioned in the comment section. And architecture semicolon. Let's quickly decode this. So we have entity name sub1. It has two input ports, input A and input B, and it has one output D out. These input output ports are integer type, and we have also specified their range as well. As we said earlier, this module is designed which can add numbers which can have the value from 0 to 9. So inputs have this range. But when you add those numbers, then you may have the D out value anything from 0 to 18. So you need to use D out integer range from 0 to 18. Although I have specified 36 here to make it simple, as we are going to use its output in the second component later in the top module. So this output can go up to 36. Well, you do not need to specify that range here for this module, but I just wanted to make this easy at the moment. So consider the range is 0 to 36 for D out. Then AND entity. Now the architecture section. So we simply said that it is adding two inputs. So the statement is D out gets the value of A plus B semicolon. And in the last, AND architecture. Okay, so now we have created the sub1 module. Now it's time to design the top level entity for our requirements. So in this slide, we are just writing the entity of this. So write entity, top level entity is port x colon in integer range 0 to 9 semicolon y in integer range 0 to 9 semicolon d out colon out integer range 0 to 36 bracket close semicolon and entity semicolon. A quick brief of this. So we have the entity named as top level entity. This has two inputs x and y. Both are integer type and having the range of 0 to 9. This range is exactly same as the range of sub1 module if you remember. And this top level entity has one output which is d out. Again integer type and with the range of 0 to 36. Now coming to the architecture body part. So we are needing both the sections here of architecture body, means declaration section and architecture body. In this slide, we are writing the declaration section. So write architecture behave of top level entity is signal sig1, sig2, sig4, sig5 colon integer range 0 to 9 semicolon signal sig3, sig6 colon integer range 0 to 36 semicolon. Now component sub1 is port a colon in integer range 0 to 9 semicolon b colon in integer range 0 to 9 semicolon c colon out integer range 0 to 36 bracket close semicolon and component semicolon and begin statement. Now, because we have internal signals here in this top module, so we define them inside the architectural declaration section. These are sig1, sig2, sig4, and sig6, which are integer type and having the range of 0 to 9. If you notice, then we have written multiple signal names with the comma separations. This is allowed in VHDL, that you can declare multiple signals in one single statement. And you can do this just by adding commas in between signals. But remember that those all signals should follow the same data type like here we did. Now because sig3 and sig6 has different integer range, hence we need to declare them separately from sig1, sig2 or sig4 or sig5. So we declare sig3 and sig6 together, which is having the same data type and integer range. This is very important to remember when declaring multiple signals in one single statement, that they should match the data type and the length of range, etc. Now we declared internal signals. And now it's time to declare the component of sub1 in this VHDL code. This component declaration also need to be written here in this section only. So all the components which you are going to use in your design, just declare all of them here in this section. Component declaration is very simple. Let's see what I have written. So this is component sub1 is port bracket start a colon in integer range 0 to 9 semicolon b colon in integer range 0 to 9 semicolon c out integer range 0 to 36 bracket close semicolon and component semicolon. Now if you notice that it is exactly same as you defined the entity of sub1. The only difference is that the entity keyword is replaced by the component keyword, because now you are declaring the component here as sub1, not the entity. So copy the text of sub1 entity and paste it here and then replace the keyword entity with the keyword component, and that's it. Rest everything is exactly same, like port declaration and component, etc. Once you declare everything for your design here, then start the architecture definition with the keyword begin. Okay, so it's time to write the architecture definition for our design. So we started from the architecture begin statement. Okay, so let me read the code first and then we will decode it. So it is begin instance 1 colon sub1 port map bracket start a equals to and greater than sign sig underscore x comma b is assigned in sig y d out is assigned in sig3 bracket close semicolon. Now coming to the instance 2. So instance 2 colon sub1 port map bracket start. A is assigned to sig3 comma B is assigned to sig3 comma D out assigned to sig6 bracket close semicolon, and in the last D out gets the value of sig6 semicolon and end architecture semicolon. That's it. Just notice the symbol here. It is equal to sign followed by the greater than symbol. So this is reverse of assignment operator. And you can read this as connected to, like I read. A is connected to sig x, B is connected to sig y, and D out is connected to sig 3, and so on. So look at the first line. Instance 1 colon sub 1. So we have given some name to this instance of component sub 1. So this means we are using sub 1 component, and this is one element of our top level entity which is named as instance 1. Now write keyword port map. Now it's time to tell that what signal or pin of the sub1 module is connected to what signal or wire of the top level entity. So look at this block diagram of component 1 connection. So signal A of first component is connected to the input signal of top level entity, which is SIG-X. Now the second port of component, which is port B, this is connected to the second input of top level entity, which is SIG-Y. Now, if you see the output of this component 1, then it is going to be treated as input of another component, which is instance 2 or component 2. And that is connected with the internal wire SIG3. So let's map the port of component 1 or instance 1. So port A is connected to the SIG-X, port B is connected to the SIG-Y, and port D out is connected to the SIG3. Again, notice the symbol here. It is just reverse of assignment operator. This simply tells what port is connected to the word signal. Like here, A and B and D out are the ports of sub1 module, and signal X, signal Y, and SIG3 are the port or signals of top level entity. So if this is clear, then let's write the component for instance 2. So it is instance 2 colon sub1 port map bracket start. A is connected to sig3 comma B is connected to sig3 comma D out is connected to sig6 bracket close semicolon. This is again very similar what we did for instance 1, but the only difference is that now the port mapping is changed. For instance 2, signal A of sub1 is connected to sig3 of top level entity. Signal B of sub1 is also connected to sig3 of top level entity. And D out of sub1 is connected to the sig6 of top level entity. And in the last, we moved sig6 data into the final output of D out. So we have written D out gets the value of sig6 semicolon and architecture. And with this, now we have completed our code for this architecture. Now let's see the whole VHDL code in one single screen. Note that we didn't copy the code for sub1 here. So it is just for the top level module. So it is entity, top level entity is port X colon in integer range 0 to 9 semicolon Y colon in integer range 0 to 9 semicolon D out colon out integer range 0 to 36 bracket close semicolon and entity semicolon. Architecture behave of top level entity is signal sig1 sig2 sig4 sig5 colon integer range 0 to 9 semicolon signal sig3 sig6 colon integer range 0 to 36 semicolon. Component sub1 is port bracket start A colon in integer range 0 to 9 semicolon B colon in integer range 0 to 9 semicolon C out integer range 0 to 36 bracket close semicolon and component semicolon. Begin Instance 1 colon sub 1 port map bracket start. A is connected to SIG-X, B is connected to SIG-Y, and D out is connected to SIG-3 bracket closed semicolon. Instance 2 colon sub 1 port map bracket start. A is connected to SIG-3, comma, B is connected to SIG-3, comma, D out is connected to SIG-6 bracket closed semicolon, and in the last, D out gets the value of SIG-6 semicolon and AND architecture semicolon. Well, there is a small mistake here in this code. Can you guess what it is? So the mistake is in the signal declaration in the architecture. If you remember, the output of instance 1, which is SIG-3, that is connected to SIG-5 and SIG-6, which are the inputs of instance 2 of sub1 component. Now the problem is SIG-4 and SIG-5 signals having the range of 0 to 9, which we have defined. But that is the output of instance 1, which should have the range of 0 to 36. So if you're going to use these signals, I mean SIG4 and SIG5 in your code, then this will give you some error in your results. And your output may not be the same as you are expecting from it. But this code will still work because we did not use SIG4 and SIG5 in our architecture. We directly connected instance 2 inputs to the SIG3, which is the output of instance 1. So let's correct this now. Correction is very simple. Just move SIG4 and SIG5 to the second declaration of signal. I mean with SIG3 and SIG6, which is having the range of 0 to 36. So the correct declaration of signals for this design would be signal SIG1, SIG2, colon, integer, range 0 to 9, semicolon, signal SIG3, SIG6, SIG4, SIG5, colon, integer, range 0 to 36, semicolon. Okay, so this is the time to quickly recall the VHDL file template once again. So we start from the library and package declaration, followed by the entity declaration and architecture declaration. This is general VHDL body, which you will use in most of your VHDL design. It is first declare VHDL libraries and packages up here, then entity. Entity name is port bracket, declare all the modules input output ports here, then bracket close, semicolon, and entity, semicolon. Architecture, architecture name of entity name is, then declare all the internal signals and constants here, then declare the components here and begin. Now define your module behavior in this section here. And in the last, and architecture, semicolon. Okay, so that's it for today. This was quite a long session, but I hope that it made you create a strong foundation of VHDL components. And I believe that you are more confident now about the VHDL components, like how to use them, where to use them, and what are the benefit of it, etc. In the next session, we will be talking about VHDL concurrent statement. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.